Good morning, my dear students. We'll continue in the third module here, that is pavement materials. Module 3, it is pavement materials. Okay, here pavement means we know that pavement, what are the materials which are being involved in the construction of pavement. So basically we are going to study about it. So the quality of the materials, how it should be, how the quality should be maintained, all those things. So in that, the first thing is the subgrade of the soil. So you know that whenever you are going to construct a road, what are the things are going to involve? First we are going to make it level the ground, then we are going to place with the boulders on a layer of the boulders, then with a subgrade soil. So that is the first thing. What is that? Subgrade soil. So that is below your pavement, below the whatever the pavement is there, that below whatever is there, that is your subgrade soil. What should be the quality of subgrade soil, how we should maintain the quality of the subgrade soil, that we'll study here. The subgrade soil is an integral part of the road pavement structure which directly receives the traffic load from the pavement layers. The subgrade soil and its properties are important in the design of pavement structures. So what does it mean? The subgrade soil is the main part, because we are having the various types of vehicles and different kind of loads. So these loads need to be transferred to the ground. Okay, so we don't know whether our ground is compacted or not. So whether it is a dense, whether we don't know the density of the soil, how it is. So it may be a loose soil, it may be hard soil. Okay, so if it is a loose soil, it may get sink or settle down. Okay, but in case of hard soil, it won't. Okay, there will be different different thickness of, or what it is, settlements are different. It is settlements are different at various points. It is depends upon the soil density. So if more dense soils, there is a less settlement. If there is a less dense soil, this is a more settlement. So likewise, we don't know the profile of the ground, and we are not knowing what will be the density of the soil. So for that purpose only, we are going to do the compaction. So to bring our soil a particular density, we are going to do the compaction. So okay, so here whatever the load is to be transferred, it transfers through the subgrade soil. So whatever the vehicular load are there, that load has been transferred to the various pavement materials, and then it is transferred to the soil through the subgrade. Okay, the main function of this subgrade is to give adequate support to the pavement, and for this subgrade should possess sufficient stability under the adverse climate and loading conditions. So here, as it is important, and it may changes based on the climatic conditions. It is at various climatic. In the summer it is different, and it is winter it is different. So here the subgrade soil is very attractive to the water. So if the water enters into the subgrade, what happens? It will get swell, isn't it? So to maintain all these things, the stability, to maintain the adequate strength is the main important in the subgrade soils. Okay, the formation of waves, corrugations, rutting and showing in black top pavement, and the phenomena of pumping, blowing, the consequent cracking of cement concrete pavements are generally attributed due to poor subgrade conditions. So whatever our roads are getting the different kind of failures, that is waves, okay, and corrugations, rutting, showing of black top pavements, and phenomena of pumping, blowing, these consequent cracking of cement concrete pavements are, these things are generally mainly depends upon the subgrade condition or poor subgrade conditions. So what are the desirable so only we need to have a good subgrade, so that we should maintain a proper pavement here. Okay, there is various desirable properties of subgrade soil for highway materials are listed here. So one is the stability of the subgrade and incompressibility, permanency of strength, minimum changes in volume and stability under adverse condition of weather and the groundwater, good drainage, and ease of compaction. The first point, the stability. What stability means? It is the ability to withhold the loads. That is our stability, and it should be stable for entire life. It is okay. That is the stability of the soil. That is the stability of subgrade. Means it should not change with the climatic conditions, or it should not change with the loads and all those things. It should be stiff enough. It should be strong enough to bear the loads, and without any failure or without any expansion of the soil, all those things. Okay, this is the stability. Next is incompressibility, and it has got incompressibility. So you just take a soil, just put some water upon this. Okay, the soil attracts the water, absorbs the water, isn't it? The soil absorbs the water. Afterwards, if you are going to put a roll on that, it will get compacted. Why it is this phenomenon is going to occur is, in the soil particles there will be a pores. Okay, if you take a loose soil, it is lesser dense. In between the particles there is a pores. That pores has been accumulated by the our water. Okay, so that the volume will be increased. When the load has been going to be applied upon that, what happens? This water from these pores get expelled, so that it will get compressed. So our subgrade should be such that whatever the load you are going to apply, it should not get compressed. That is incompressibility. And permanency of the strengths, means the strength whatever we are designing at the beginning stage, it should be there throughout the life of the road. So that is permanency. Minimum changes in volume and stability under adverse conditions of weather and ground. There should not be any changes in a value and stability. So these things are mainly because of the climatic conditions and good drainage, and it should be always be provided the good drainage for the good drainage. Otherwise, the water is going to enter into the subgrades. Okay, so proper drainage has to be maintained, and ease of compaction. These are the properties of the subgrade soil. Next, the tests used to evaluate the strength properties of the soils may be broadly divided into three groups: shear test, bearing test, penetration test. So one thing is strength should be there. So how we should confirm that this subgrade is having a good strength? So that we are having three different types of test, that is shear test, bearing test, penetration test. So we know that what is shear. Okay, it is unbalanced force, isn't it? So shear test means it is going to apply in the vertical directions. Shear tests are usually carried out on relatively small soil sample in the laboratory in order to find out the strength properties of the soil. A number of representative samples from different locations are tested. Some of the commonly known shear tests are direct shear test, triaxial compression test, and unconfined compression test. So these are the various compressive tests. What are those? Shear, triaxial compression, unconfined compression, direct shear test. So this direct shear test we are going to perform in our where geotechnical lab, isn't it? Bearing tests are loading tests carried out on the subgrade soil in situ with a different load bearing area. The result of bearing tests are influenced by variations in soil properties within the stressed soil mass underneath, and hence the overall stability of the part of the soil mass stressed could be studied. Penetration test may be considered as small scale bearing test, in which the size of loaded area is relatively much smaller and ratio of the penetration to the size of loaded area is much greater than the ratio in the bearing test. So based on the grain sizes, we are having the different types of soils. The soil fraction larger than 2 mm size is called as gravel. The soil fraction larger than 2 mm size is called as gravel. Between 2 mm to 0.06 mm it is sand. Between 0.6 mm to 0.02 mm size it is silt, and less than 0.002 it is clay. The size which is less than 0.002 mm size is soil particles whose size is less than 0.002 size is called as clay, and the size between 0.002 to 0.06 that is called as silt, and between 0.06 to 2 mm it is sand, and about 2 mm it is gravel. Highway Research Board classification of the soil. Based on the Highway Research Board, we are again having the different classification of the soils here. This also Highway Research Board is also called as American Association of State Highway Officials, AASHO, American Association of State Highway Officials. Classification of Revised Public Road Administration. Soil classification system. Soils are divided into 7 groups, A1 to A7. A1 to A7, that is A1, A2, A3 soils are granular soils. A1, A2, A3 soils are what? Granular soils, and that percentage of fine passing is 0.074 mmCu, being less than 35, and A4, A5, A6 and A7 soils are fine grained or silt clay soils passing 0.074 mmCu, being greater than 35%. Okay, so based on this we are going to classify the soils, that is A1 to A7. So what is that? A1 to A1, A2, A3 soils are granular soils. In that, percentage fines passing is 0.02 mmCu is 35%, less than 35%, and if it is more than 35% it is A4, A5, A6 and A7 soil. Okay, we will go on one by one. What is A1 soil? A1 soils are the well-graded mixture of stone fragments, gravel cores, sand, fine sand, non-plastic or slightly plastic soil binder. Soils of these groups are subdivided into 2 subgroups, A1A consisting of predominantly of stone fragments or gravel, A1B consisting of predominantly of coarse sand. A2 group soils include wide range of granular soil ranges from A1 to A3. Groups consisting of granular soil up to 35% finds of A4, A5, A6 or A7 groups. Based on the fines content, the soil A2 groups are subdivided into subgroups of A2, 4, A2, 5, A2, 6, A2, 7. It is based on the fines. Again, the A2 group has been classified as like this. A3 soil consists of mainly uniform graded medium or fine sand, similar to beach sand or a desert blown sand. Stream deposited mixture of poorly graded fine sand with some coarse sand. Gravels are also included in this group. These are the different soil classification: A1 to A2, A3, A4, and A5, A6, A7. Now, based on this, we are having the quality of soil sample, how it is, the separate soil. We are having the CVR test, that is California bearing ratio test. California bearing ratio test. You just see here the figure, proving ring. So here this is your proving ring. It has been attached with a plunger here of 50 mm dia. This is proving ring. You are having in this, we are having the readings, and this is plunger. This is surcharge weights. This is the soil sample inside, and this is inner diameter of the mold, that is 150 mm diameter, and total height it is 127 from this to this it is, and these are the base plate, and this is dial gauge measure to measure the penetration. So here what happens is, we'll detailedly discuss about this here. This is the mold. In this we are going to compact the soil, and we are going to attach we are going to place this surcharge weights, and the plunger is going to attach here. The loading has been applied. As the load applied, there will be a movement, movement in the dial gauge. So that dial gauge reading we are going to note it down. Okay, for this we will detail study here how to perform. This is penetration test developed by the California Divisions of Highway for evaluating the stability of the subgrade and the other pavement materials. The test results have been corrected with flexible pavement thickness requirements of a highway and the airfield. CVR tests may be conducted in laboratory on prepared specimen in a mold or in situ in the field. To how to perform in the laboratory, it is, we are having CBR apartment consists of cylindrical mold, 150 mm dia, 175 mm height. This is your cylindrical mold. This is cylindrical mold. It is 150 mm dia, 175 mm height, and 50 mm collar. Here we are going to have the collar here. Above that, detachable spacer disc of 148 mm dia, spacer disc, and 47 mm thick, used to obtain the specimen exactly 127 mm height. We are going to get exactly a specimen of 127 mm. Then the loading machine, compression machine operating consists of operated at constant rate of 1.25 mm per minute. 1.25 mm per minute. Loading frame with cylindrical plunger, 50 mm dial gauge, and dial gauge for measuring the deformation due to application of load. Type of compaction, we are having light compaction and the heavy compaction. Number of layers in light compaction 3, number of layers in heavy compaction is 5. Weight of hammer, it is 2.6 in light, 4.89 in heavy. Fall is from 31 centimeter, here fall is from 45. Number of blows given is 56 in both the cases. So now we'll study the how to perform the CBR test. How to perform the CBR test. This CBR test has been performed on the undisturbed soil sample. Undisturbed soil sample. Undisturbed soil sample means whatever the ground soil is there, we should not disturb it. Before testing it, we should not disturb it. Then how to take this undisturbed soil? How to take this undisturbed soil? Correct? Okay, this your CBR test is going to conduct on the what undisturbed soil sample. We are going to collect a soil sample of about 5 kg, which is passing through 20 mm sieve and retained on 4.75 mm sieve. That much of such 5 kg of soil sample need to be taken. The soil is mixed with the water up to optimum moisture content. So little bit of water has to be added, especially it should be added up to optimum moisture content. We should find out the optimum moisture content for that soil. Okay, optimum moisture content of the soil. So that much of water we need to add it and make the mix. The spacer disc is placed at the bottom of the mold. So as I have told you, we need to take a mold of 150 mm diameter, 175 mm height with a collar height of 50 mm. Okay, and a detachable base plate. So all these things need to be kept on a table, and then the soil is going to be poured on it in layers of how much layers. It is again depends upon the whether it is a light compaction or a heavy compaction. If it is a light compaction, 3 layers with 2.6 mm 6 kg of hammer. If it is heavy compaction, then it is 5.5 kg of this thing and 5 layers. Hammer is of 5 kg, 4.89 kg and the number of layers it is 3. Okay. Then the moist soil sample is to be compacted over this in the mold by adopting the either IS light compaction or heavy compaction. Based on which method we are going to apply, we are going to get the different answers. So whichever the one we need to choose it, lighter or heavy compaction. So for light compaction, it is 3 equal layers of a compacted thickness about 45 mm by applying 56 evenly distributed blows from 2.6 kg of hammer. If it is for heavy compaction, 5 equal layers of compacted thickness up to about 26.9 mm by applying 56 evenly distributed blows from 4.89 kg of hammer. After compacting the last layer, the collar is removed and the excess soil above the top of the mold is evenly trimmed off by means of straight edge 5 mm thickness. This you did in your geotechnical lab, I think. GT lab. GT lab, it is there. In which semester you are going to have GT lab? I think in the 5th sem itself. Yes. Okay, in GT lab also you are going to do this light compaction and the heavy compaction. Okay, this is what the procedure of following the light and heavy compaction. After compaction, the last layer, the collar is removed and the excess soil above the top of the mold is evenly trimmed off by means of straight edge of 5 mm thickness. Clamps are removed and the mold with compacted soil is lifted, leaving below the perforated base plate and the spacer disc which is removed. Then the mold with compacted soil is weighed. Then after removing that, the whatever the compacted soil is there, that we need to be weighed it. Then filter paper has to be placed on the perforated base plate and the mold with compacted soil is inverted and placed in position over the base plate. Now again the clamps of the base plate is tightened. Another filter paper is placed on the top surface of the sample and the perforated plate with adjustable stem is placed over it. Now the surcharge weight of 2.5 or 5 kg are placed over the perforated plate and the whole mold with the weights is placed in the water tank for soaking. It means whatever the means in the mold itself we are going to place this soil sample in a water for about 4 days, that is for about 96 hours, by applying the dead weight upon that soil sample, okay, upon that the mold. And then the dial gauge has to be attached to that plate. So likewise here, see here see the whatever the soil sample you are going to collect, this will be there here. We are going to place one perforated paper here and above this base plate, and at here also we are going to place. Then we are going to apply a surcharge weight here. Then the dial gauge has to be made 0 and it has to be attached to the surcharge plate. Okay, then this whole setup has been placed in water for 96 hours, means up to 4 days. Afterwards what happens is, in the 4 days the whatever the water is going to be, absorbs. In the 4 days some of the water needs to be absorbed by the soil. Okay, so that there is a readings we are going to get in this dial gauge, isn't it? When this water absorbs by the soil, it will swell, isn't it? If it swells, means automatically the readings will going to be changed. That readings we are noting down. Correct. The initial dial gauge reading is recorded and the test setup is kept undisturbed in water tank to allow the soaking of soil specimen in for full 4 days. Final dial gauge reading is to be measured and the expansion and swelling of the specimen due to soaking. Final dial gauge reading has to be noted down. The soil measurement assembly is removed. The mold is taken out of the water tank and the sample is allowed to drain in the perpendicular position for 15 minutes. Surcharge weight. Perforated plate with stem filter paper are removed. The mold with the soil subgrade is removed from base plate and is weighed again to determine the weight of water absorbed. Then the specimen is clamped over the base plate. Surcharge weights are placed on the specimen centrally such that the penetration test could be conducted. One thing is, after swelling we are going to note down the initial dial gauge reading, final dial gauge reading, and we'll get the swell. Okay, and afterwards we need to determine the penetration. The penetration plunger is seated at the center of the specimen and brought in contact with the soil sample. In the case of load reading starts decreasing before 12.5 mm penetration, the maximum load and the corresponding penetration values are recorded. When the penetration has been placed on that soil sample, okay, what happens is as the load increases, the penetration decreases. It goes on penetrating into the soil sample. So, in case load readings start decreasing before 12.5 mm penetration, means if the load reading decreases before 12.5 mm of the penetration, the maximum load and the corresponding values are recorded. Means maximum loading value and the maximum penetration is to be recorded. After the final reading, the load is released, the mold from the loading machine, the probing ring calibration factor is noted so that the load dial gauge value can be converted into load in kgs. Calculations. Here, swelling or expansion ratio is calculated from the formula. Expansion ratio is equal to 100 df minus di divided by h. df means it is final dial gauge reading, di means it is initial dial gauge reading divided by height of the specimen. Final dial gauge reading minus initial dial gauge reading divided by height of the specimen into 100 is what? The expansion ratio. So this is your CPR test. So go through the once again the notes also. If you feel any difficulty, you can contact me.